everyone. Okay, the music is really cool, but unfortunately I do have to turn it off so you can hear me. So, good evening everyone, and my apologies for the delay. The delay was sponsored by USB, or actually a microphone. Oh wow, that's crazy. That's funny. The sound on YouTube was like turning on and off and on and off. Anyway, yeah, but delay was sponsored by USB problems, but after a reboot suddenly they disappeared, which is a good thing. So I already complained last time about it. I guess I shouldn't do it again, but I still haven't found the time to fix my problem and actually order a new USB hub. Therefore, yeah, I'm using temporary solutions which are, yeah, well, not great. Anyway, so today's moderator is KrzaQ. You can see his nickname somewhere here. Yeah. If you have any questions during the stream regarding or whether they're on topic or off topic, you can ask KrzaQ, or actually you can tell them to KrzaQ and KrzaQ will pass them to me. If you have C++ questions, actually then just ask KrzaQ, don't bother asking me because he's way better in C++ than I am. Yeah, so today's topic is going to be the tooooo challenge from the HITCON CTF. It's actually a misc low-level ARM64 ROP challenge, which is quite fun. So I wanted to showcase it, and I wanted to show it how I solved it, and my approach was semi-automated. Keyword here is semi-automated. It wasn't fully automated, but it was pretty automated anyway. Yeah. So before we get there, I guess if there are any questions, I can go through them. Marble, you have hair. Yes, I do have hair. I usually have it tied, so it looks like a little I'm bald, but yeah, I actually do have hair. So, okay, the usual things. So, where is this? Here we go. Yeah, this is KrzaQ's blog, dev.krzaQ.cc. Totally check it out and totally try to convince KrzaQ to actually post something new. He usually has really amazing write-ups, so yeah, too bad he doesn't post that often. Apart from that, there are some CTFs which we took part in, we as in Dragon Sector. In all honesty, I only solved 2 tasks on both CTF, 2.5. Well, the last task wasn't really solved fully. And they were HACLU and HITCON, both really high-ranked CTFs. We managed to win HITCON actually with a pretty comfortable margin, though it was like the last 4 hours of the CTF. We like finished one task after the other and skyrocketed with the score. HACLU we didn't win. We were actually the runner-ups, and still it's a pretty decent gain of points to the global ranking, which means we are currently again ranked on the first place. But do not read too much into it, because actually PPP will get a lot of points from the DEFCON CTF in Vegas, which I believe they won, or were like, I think they won it, but the ranking is still not on the CTF time for some reason. So yeah, they are actually not far behind, or even above us if you take everything into account. Well, actually, it's complicated, but we are pretty close. Okay, so I guess there was one thing I wanted to mention about HACLU, because there was an interesting case on HACLU regarding CTF tasks, and I guess the best way to show it was this, yeah, like some votes that the rank of a CTF should actually be pretty low or lower than it was, including, well, as you can see, neither me nor Redford were amused, and the problem was that there was a Stegano challenge, like Steg 0, which was actually unsolvable. But the funny thing is that it was intentionally unsolvable. It was included as a joke on the CTF, but the task itself looked really like a real task. So it was, I think the source code was actually in somewhere, MSM from P4 had a write-up, like really amazing write-up, really funny write-up about it. So let me show you the source code of the challenge. Okay, P4 and write-ups from P4 stack here, read write-up. Here we go. Okay, so this is the source code. Get some data from the view random, then get the SHA to 200 SHA-512 checksum of that file of the data which you got and put it in this file. Then use tar on this to create a tar file from the random data. It's random data, there's nothing inside, it's straight from the view random. Then bezip it, then 7-zip it. I actually have no idea what happened to this because I don't believe I saw... Yeah, it was bezipped, but it wasn't 7-zipped. I'm pretty sure it wasn't, so maybe they used the incorrect file. Oh yeah, as you can see, when they move stegano tarbz, so this file created by this command, they totally ignore this command. So this wasn't important. Rename it to .jpeg, and then they wanted to create a comment, there is no flag, with a password, there is no flag for the zip file. But as you can see, the password here is actually E, so that was a little bit of a failure, but that didn't matter at all. So the password for the archive, for the zip archive, was E. And the comment was there is no flag. Yeah, and I guess this is further scripts like another, the flag was random, it was not included in the challenge itself. So the description for it was, well, it doesn't really matter. There was a hidden HTML comment, hidden, so we had to look in the source code of a page which said that this is a fake or something like this. And the comment again was there is no flag, and if you asked the admins on the channel about it, they said read the description of the task. And that's the only hint they gave on IRC that I saw at least. Now, the problem with this is that on CTFs, it's pretty common to claim that in the description of a task that, hey, this task is not solvable, you're not going to find the flag. So seeing there is no flag, or like the HTML comment saying this is a fake, you might believe it, but usually the smart thing to do is not believe it and actually try to solve the challenge, because why would anyone post a challenge which is not solvable, right? Additionally, if you're thinking about steganography, Jesus, then there are two kinds of steganography challenges. The first kind of steganography challenge is file format based, where you hide data, hide the flag in the intrinsics, the complexities of the file format itself. Not the data, which is stored in a given file, but the file format itself. And there is the second kind where you hide it in data, like hiding in bitmaps, hiding in WAV files, and so on. So the second category isn't really loved on CTFs, but the first category is pretty okay. I actually really like it. So yeah, seeing like a bezip2 file, a zip file, and a tar file, there are a lot of places where one can hide a flag in a zip file, in the deflated stream, there is a place, if the stream is encrypted, there is a place where you can hide a flag there. Then the bezip2 and actually the deflate stream itself, which is halfman plus lz something, there are ways to hide some data there as well, like the shape of a tree, or how you use the tree, or like how lz chooses which piece of data to link to. You have to know the algorithms really well, but you can hide data in the compression layer. So when it gets decompressed, there is no data. You cannot see the data as plain text in the compressed layer, but it is there. So yeah, we spent around like 30 hours in Dragon Sector trying to solve this task, and I know that our teams also did the same. And when the end of the CTF came and the admin showed the source code, we were like, yeah, this should not happen. This should not have happened on a high-profile, high-ranked CTF, but there is a challenge which is just a red herring, which makes people waste time. And especially that it looked like a really fun steganography challenge. So yeah, we complained. As you saw, I've written that a good CTF overall, however, the inclusion of a fake unsolvable task disqualifies it as a high rank CTF, in my opinion. That was my opinion, and is still my opinion at the time. So if you're a CTF creator, please do not include fake tasks. We have enough problems solving real tasks, right? So why do you want to make it even harder? Flagsfingers actually did the right thing, and the Flagsfingers were the organizers of HITCON. What they did is they published a post-mortem on Twitter, on their Twitter account. A post-mortem in IT is basically a write down of what went wrong and why did it went wrong and how to solve it. It's quite an interesting read. If you go to their account, Flagsfingers, you can read all about it. And in the end, basically, they explained like what happened, like that it was a joke, yeah, it shouldn't have happened, and so on. And they basically said that they will make sure that they will not do it again because obviously it wasn't well received, right? So yeah, that's a good statement from them. I really liked that they posted it, that they addressed the situation, that they actually, didn't ignore the feedback. So props to them. And actually, after reading this, I changed my vote on CTF time to 55, like greatly increasing it, because I said that I'm happy with the resolution. I was submitting my vote. So yeah, in the end, I believe the weight is not going to fall. So yeah, it finishes tomorrow, so it won't fall that much. And it's a really interesting case for on the CTF scene. I guess something we as the scene learned again from this, which is a good thing. Yeah, so that was HITCON, and HITCON again, a pretty cool CTF, a really cool CTF. Apart from that one problem with stack 0. Now HITCON was another thing. HITCON has almost maxed out rank. I think there is like one CTF or no CTF at all which reach the 100 points, and 100 points are the top ranked CTF, like the best CTFs there are, the best competitions there are, and there are not too many of them. I think there's like 5 per year, something like that. That includes, by the way, will include next year the Google CTF qualification round as well, which I'm super happy for. And there are some prizes. We actually managed to win it with a pretty comfortable margin of points, 1,500, and yeah, 5K and qualification to DEF CON actually. So Dragon Sector has already qualified, which I'm also super happy about, and congratulations to all the players from Dragon Sector. PPP was second, and BF Kinesis was third. These are folks from Taiwan, from the same country as the organizers of the CTF. So yeah, well done. It's always awesome as the organizers to see a local team doing really well. And I wanted to show you a task today from this HITCON CTF, which this is by the way which tasks were solved. Yeah, one of our players did like a great job on the hexagon series. That was pretty cool. He got like first blood on 3 of them. We got some... First blood is when you as the team solve a challenge as the first team during the competition. So before your submission of a flag, nobody else submitted the flag. There are usually no additional points. On some CTFs there are additional points, but usually there are none. And it doesn't matter, but it's just, fun metadata to see. Anyway. So yeah, the task was called tooooo, and before we get to that task, let me see if there are any questions from you. There are actually 4 questions, so let me quickly go through them. The questions will show, oh wait, here, yeah. First question is that possible, and how that malware may stay undetected by the user, even a technical person, and how many such malware programs are there in practice? That's a good question. In malware theory, there is this saying that if malware runs with higher privileges than whatever tool you are using to detect it, then the malware may stay undetected. And that's true. So for example, if you have malware running in kernel mode in ring 0, right, and your detection tool is purely userland, there are ways for malware to stay undetected. And now that doesn't mean that the malware will always be undetected. What that means is that there is a chance to achieve that actually, and a pretty high chance if you know what you're doing. And this is just because having higher privileges, you can usually emulate the results of a detection. So, for example, if the malware consists of a file which is driver.sys, like a typical driver file, right? And the detection is check if the file exists and then check if the file has a given signature. What a malware running in kernel mode could do is could actually hijack or hook the syscall made to check the file existence and reply that, yeah, the file doesn't exist. And if your tool is on user land, the tool can only believe the kernel, right? There is no other way to check if a file exists from user land than actually asking the kernel to check if the file exists. That's how operating systems work. And the same goes upper, right? So if you have malware on a hypervisor level, this was the blue pill discussion from 2005, a pretty prominent discussion, I guess, where it was basically discussed if you can create a malware on the hypervisor level that is not detectable from the operating system level. It's actually hard. It's surprisingly hard. And so on and so on. So if you have like something running in management engine, then you might not be able to detect it from kernel mode. Management engine is, I guess, a different story, but like, let's say system management mode or SGX and so on. So yeah, the rule of thumb is if you have something running with higher privileges, then you should attempt to detect it with having at least the same, but ideally higher privileges than that. Now, so I guess, yeah, that's the answer to that question. That being said, what I've described is an ideal situation for a malware, but a malware might still have some side effects which are detectable with lower privileges, and usually that's what you rely on in malware detection. You rely on not detecting what the malware does, but some side effects of its existence. And that's also might be doable on, like for example, I mentioned that you have to ask if a file exists, and then a malware could actually hook the syscall and say if the person is asking for this file, then say always no, it doesn't exist, right? And you can do a timing check on that. Like, for example, usually when answering a question about a given file that doesn't exist, the kernel replies in 0.1 or 0.01 millisecond. But in this case, it always replies with 0.05 milliseconds. So what's up with that? Perhaps something is hooking and the file actually exists. So it's a pretty interesting discussion. You might want to look into rootkits, like ROOT kit, because rootkits are the things which are hiding in the system. I want to ask about anti-cheat technology and the use of rootkit in that technology. Yeah, rootkit. Anyway, that's an interesting discussion actually, and because it's like this: anti-reverse engineering, anti-cracking, and malware are two sides of the same coin, as in the same techniques used by malware authors are used by anti-reverse engineering folks. So yeah, there were cases in the past and still exist today where a given anti-cheating or anti-reversing software tries to act as a rootkit, as in hide from an active, from a person who actively attacks it. And the community has been pretty outspoken that should not happen, yet there are still like creators of games and so on which actually use kernel land rootkits who do really funky stuff to prevent cheats. And in the end, I don't think that's actually solvable this way. Cheating is not solvable using rootkit-like approach, using kernel level drivers, because I mean, even if it's a kernel level driver, it's always you have physical access as an attacker, as a person who wants to create a cheat, right? Who wants to bypass it. You always have physical access to the machine. If you have physical access, it's usually game over. Usually there are techniques to subvert whatever mechanisms were used. With SGX being a new thing, which makes it a little bit harder though. But usually that's how you think about it. And yeah, so you cannot solve cheating this way. You can use detection, and if you play any online games, you know how that works, how well that works. In the end, a better solution might be to, you might remember the OnLive service. It was streaming games through the internet, so the game was running actually on some server, and you'd basically just stream video from that server of the game and stream back input, like keyboard input, mouse movements. It obviously introduces some lag to the game, but for most of the games it's playable, you know, maybe not for Counter-Strike on professional level, right, but like other games that might be playable. And in that case, if the game is running on a server which you do not have physical access to, that's way better in terms of way easier to defend from cheating. So I think that's actually the future of anti-cheats. You still will be able to do some stuff. For example, based on the video you receive, you will be able to have ML, like machine learning based algorithm, which actually says, oh, here's the enemy player, and then submit mouse movement to actually point at the enemy player, which might give you some advantage, or just highlight the enemy player on some like really bright green or really bright yellow, so that they are easier to spot. But it changes the game, and like, yeah, that might be a little bit harder. What happened to English version of your book? It's still in the making. I just am too busy with other stuff to finish it. But it's still in the making, and I still have high hopes of eventually publishing it next year, early next year. Well, maybe not early next year, but next year. Regarding HITCON 2018, how to do unexecutable, I'd really like to know, but there are no write-ups. I have no idea. So yeah, I didn't solve that challenge, so I have no idea. Check on the scoreboard which team solved it and email the teams who solved it. They usually are quite happy to share the solution. Can I solve another task, another easy task from HITCON? Probably not today. I don't want to make too long of a stream today, so probably not today. Maybe on next live streams. Cool. So let's actually get to hacking. Okay. So you received actually a directory with 3 files. Let me open the console to show you the files. Here we go. Yeah. You received the executable, 10 kilobytes. That's really good actually. That means it won't be too much reverse engineering. Then the libc. Having libc usually helps if you have to do return-oriented programming. It's sometimes it changes makes the tasks easier. Other times it doesn't matter at all, because you can guess the libc, like have educated guesses on what libc is being used anyway, or just leave the libc. So it's courtesy of the challenge creator to actually include libc, though if they want to make it hard, they don't. And this is the dynamic linker. So yeah, you know, like when you execute a dynamic executable on Linux, then it actually will call this file, this program, ld something, ld linux, to load all the libraries for the file. Cool. So that's the challenge. Now, the funny thing is, if you open the file, well, maybe not this file, open the executable file, and you look at the name of the dynamic linker, it's usually a string which is here. So this is the name of the dynamic linker. You can see this, yeah, I can zoom it. arch 64 or arc as in architecture 64. This actually is the ARM64 architecture, so it's ARM64, which means it's not an x86 challenge, which makes it a little more funny. Now, actually, starting this challenge, I already knew what the challenge will be about, because last year, a year ago, there was another challenge called tooooo, like spelled differently but pronounced the same way, which was a challenge where you had to find 2 ROP gadgets on x86 that spawned you a shell. And the problem was that the environment, the registers were randomized, so yeah, like here, have this huge executable and try to find 2 gadgets, only 2 gadgets that will give you a shell. Some of you might know about the magic gadget, that is a 1 ROP gadget which exists in libc, sometimes in multiple places in libc, which actually spawns you a shell, like just 1 gadget, right? But on 64 bits, depending on the compilation options and so on, usually you cannot use the magic gadget. So, and that was the case last year as well, so you actually had to find 2 gadgets to be able to execute something. Now, this challenge is basically the next version of this challenge, but on our AR64 architecture. So yeah, that's what it's about. Now let's open it in, let's try to run it and let's open it in IDA. Okay, so to run it, you have to have QEMU user installed. If you have QEMU user, you know, like QEMU installed, then you can do tricks like tooooo, and the kernel will actually pick the proper QEMU user to start and emulate this program, so I can do just this. It actually started, well, it didn't start execution, it actually went to kernel, and the kernel read it and said, yeah, like, this file is missing. But that's fine, because the file is actually here, it's just named differently. Initially, I thought it's not here, and I downloaded the proper library files from Ubuntu, but it's actually here, it's just renamed. So let me rename this. Let's remove this to this. Okay, now I need it to be in this directory, but that doesn't really matter, because what I can do is I can run this, and I run the dynamic linker and give 2 as a parameter, and that works too. So now it says, it actually executed and says, yeah, libc is missing, what's up with that? And that's again because the file is just named in a different way, because this is the real name of a file now, and libc so is usually a symlink, but we don't care about it, we can just rename it. And we can run it, and it still says the same, because as you know, libc will not be looked for in this directory. What we can do instead is we can pass a parameter called library path, which does exactly what the environment variable does, as in we can tell it, yeah, look for libraries actually here, path here, and now we can run tooooo, and it runs. Now it outputs something, and the first thing to do, I guess, is to try to figure out what does it output. Let me run another Linux console. Okay, here we go. And oh, that actually will not work as I intended to do, because it's we need to remember that it's not running natively. It's actually running remotely, not remotely, emulated in an emulator, right? So I wanted to do just, you know, look in the proc pid maps to take a look what's under this address, but we'll have to do it a different way. What we can do, if we just run it with QEMU, QEMU R, if we do help, there are some interesting helper functions which might help us the analysis. For example, strace, and strace will do what strace does. So let's do this, and then let's use the command line we already have. So I'm going to copy this and the arguments, and yeah. And it doesn't really work for some reason. Why don't you work? Oh wait, 2 little O's. That's funny. Okay, now it works. So yeah, we could probably like derive from the mmaps here where each library is placed, but we don't have to do it. Then as we can see, it actually opens the vrandom, which is already interesting. It reads some stuff, then it writes some stuff, then it allocates some memory, and it reads some more stuff. Like this is actually 3000 hexadecimal. And then it reads 48 bytes from 0 from us, which is our input. So this is one way to look at it. The other way is obviously to run it, to open it in IDA. So let's do just that. If you don't know what a rob gadget is, don't worry, we'll get to that. Okay. And yeah, we have to find the main. It doesn't contain the usual symbols, so we'll have to find the main. I think the way I did it was actually I went through. It's probably one of these offsets, like one of these functions. It doesn't look like this one. Yeah, it looks like this one because we did see that the vrandom was open, so it is this one. I do not have the decompiler for ARM64, but I do have the file generated by the decompiler, and we can look at it. I guess we can look at it now and then get back to the disassembly, but just to take a look what's actually being printed, what is the address what is being printed, as you can see is standard output pointer. Do not look at the instructions at all. I mean, I do not know R64. I think I programmed a little for it, but I do not remember it by heart. Like I know x86 by heart, I do not remember this by heart. It doesn't matter. What matters is that printf with these arguments, and this is another argument, and then there's an nmap, and these are the arguments, right? So just read it like this, and totally don't care about the assembly part of it. This is not really important in this challenge. So just a pro tip how to reverse engineer without reverse engineering. Yeah, so if we open libc in IDA, and we do have to do that actually, because that will be super useful at some stage, so let's do that. Okay, it says it contains some relocations, which is not supported by Hexray. This will take some time. So, but yeah, I guess the point is that standard output std out is actually a file object, like file std out, or actually no, like std out, like this, somewhere in memory, and it prints out the address of this, like where is this located. Now this is located in libc, which means that if we know in libc where is this, we know on which address is libc, and it makes our life easier if we know where in memory libc is. Use radare. I'm looking at the questions. Why not find the main in the arguments for lib start main? That's just what I did, by the way. These were the arguments of lib start main. Is it possible to set a breakpoint on main if you are running a stripped p position independent binary? Yes, but you do not type break main, you type break asterisk and then the address of main. That's the difference. Use Radari2. No, I'm so not using Radari2. Okay, so did this finish? No, it's still running. So before it finishes, let's actually start coding the exploit. And by coding the exploit, I don't mean writing the full exploit. I mean just starting to connect to the challenge and then do parse this, what is outputted here, and then subtract the offset in libc, and this gives us the beginning of libc, which will be needed later on, I expect. And then when we have this, we can, and like it actually finishes, we can get back to figuring out what to do. It might seem a little out of order, but usually it's required anyway, so it doesn't matter when you do it. I'm going to use my pawn base as I always do, but I failed on copy pasting it to the correct directory. Okay, here we go. Okay, we will be using almost everything from this. We will not be using x86 registers, so I do not care about that. Let's remove it. we will be, capstone and keystone will not be needed, unicorn will be needed today, so okay, now we connect to, I actually, give me 1 second, I need to log in into HITCON. The CTF servers, I think, are still online, so we can actually solve the challenge. Really solve the challenge on the server and not just fake it locally. Okay. Okay. So this is the host and the port from HITCON. So let's replace it. Yeah, perfect. I'm actually going to leave this so I can comment out and comment in depending on whether I want to test something locally or maybe just go and test it remotely. Now, okay, so we connect. We do not care about interactivity at this point. What we do care about is receiving the end of line, because again, if we look in IDA, there is the end of line character here, so we want to receive all the traffic. So receive until all the traffic until we get the new line, and this is going to be std out address. Okay, so assuming that we actually received it, we want to strip it because we don't care, and we also want to convert it to... Do they prepend it with OX, by the way? It's prepended by... I don't see it. Let's just run it. Without test choice. Yeah, it's prepended by OX, so I do not care about OX, whatever is stripped. I do not care about the first 2 characters. And it's actually hexadecimal, therefore I need to use the 16 here. And this gives me that address as a, like this string converted to an integer value. Now, if I'd already finished, we can, yeah, it did finish. We can find where the object is, std out. Oh, I guess the best way to do it is to look for, well, maybe not get character, put character, function put char. And in the function, yeah, as I thought, there will be a reference to it because, well, that function is a reference to it. So here we go. 648 is the page offset where it's located, so we can actually check if this is the right address. But it's not the right address. The page offset here is different, right? Therefore, we do not care about this, we care about this object probably. Which makes sense, right? Because this is just the pointer and this is the real file object. And 560, the offset matches, this is the correct address. So this is the address in libc. The libc is actually loaded, as you can see, to offset 0, which is great for us. It's actually amazing because we do not have to do any math related where is the start position. We just subtract to get libc. We just subtract from std out address this value, and we get the beginning of libc, where its beginning is in memory. So we can actually brag about it, but we found the address, or libc is at this address, libc. And then the connection gets closed. Is actually not the proper way to close a connection. Shut down socket. Shut for RD, RD var. Yeah. I was thinking like SD something something because Windows actually uses SD, but I think that's the proper way to do it. Let's run it, and it's running, and we got libc on this address. Is this correct? Actually, I do not know if this is correct. Let's output what is being given here. So let's call it line, and ln is equal to this, and then let's output it because I might have made a mistake somewhere. Yeah, the FF doesn't look correct. Maybe the challenge server isn't working in the end after all. Let's try to connect it. No, oh, it actually is correct. That's funny. Yeah, and that's a really weird address, but okay. I mean, yeah, whatever. So print ln. Oh, that's why I didn't print. Okay, so that's fine. it actually works. We are getting the proper address of libc. So we have the libc address, and now we need to figure out what to do, what next to do. Now we can read the assembly code. Well, actually not the assembly code, but what's actually being called here. But I guess I can spare that to you. Basically, what's important is that we're going to call read check, and we're going to read. Well, we saw it, I guess, right? We really saw it already in this. It's going to read 48 bytes. Now, it's going to read the 48 bytes into... sorry, I'm going to move the libc for now. Yeah, and it's going to read the 48 bytes. This is the number 48 into this place in memory. This is the function, again, which is calling read check with descriptor 0. So it's reading from standard input the amount which is specified here, 48 bytes. 30 hexadecimal is 48 decimal. And it's reading it to this memory offset. So if we actually go to this memory offset, it points to some other memory offset, and this is actually the buffer which is being read. Now, if you count correctly, starting from here to the beginning of these two pointers, it's only 20 hexadecimal bytes. Therefore, these two pointers, I actually know they are pointers, will be overwritten. So the end of reading is here. And these two pointers are being referenced in these two functions. So that's actually quite interesting. So what one? Sorry, what jeden, right? Jeden is one in Polish, if you're wondering. And now we need to take a look what's actually going on here. This is just some initialization, like disabling buffering and creating an alarm. But it gets code, so I don't care. Let's look here. Here it might be a little more interesting. It actually fetches it and puts it in some registers, and then calls some function which is not really specified, like this function, x4 function. Where does it get the x4 function actually? BLR is actually like, wait, IDA is behaving really weird. Okay. BLR is like branch link from a register, which we translate to call a function, where the function is specified in the register. And if we look at the register, it's actually being, yeah, I'm sorry, I need to restart IDA. IDA behaves really weird. I know I'm trying to reverse it pretty fast, because reverse engineering this challenge is not the core of this challenge. That's why I'm going pretty fast through it. Let's look what is actually being... Where is this being assigned? Oh, it's assigned here. There's some unknown f. Let's look what's here. I don't know, it looks like some data, but I'm actually going to click C, and oh, it's actually some code. And as you can see, this code does some interesting stuff. It moves, actually it moves x1, the first parameter, to the stack pointer register. These are the arguments of the functions. Then x2 to x25, x3 to x26, and then it loads two registers from the stack pointer, then stack pointer plus 10, plus 20, and so on. So it basically reads the content of these registers from the stack, and then it calls whatever was in this argument, like x25, right? So this part, and x26. BLR, again, is call the function for which the pointer to is in this register. And then it does something, and this is a sys call. So this basically is exit, if you're wondering what this is. So it sets the registers and then calls these two functions. Now, if we go back to the code again, and this is the call to it, you can see that x0 is actually like the third argument, the function which is going to be called, is what we can override in memory, and the same is with x2. And x1 is actually being set to some content of a local variable, and if you would actually read the code, you'd find out that this is points to memory allocated by mmap, which we saw, the 12 kilobytes, right? 3000 hexadecimal, as I did mention. And into this memory later on, there was some reading done. And reading was done from, where did we get the data? 28 and open 28, yeah, here. So the memory contains random data. And the stack pointer is going to point to the random data, to the random section, and the registers are going to be filled with random data. And then our two gadgets are going to be called, the things which we can override. So this is this task, basically. This task, again, is fill some data, override these two addresses, which are later going to be called with gadgets, and the two gadgets will be called one after the other, as we saw. It's actually not a function. As we saw here, you can make a function out of it. Yeah, one after the other, and they need to spawn a shell for us. So this is the task which we have at hand and which we need to solve. Which gadgets to call? Now, what is a gadget in this case? And what is a rope gadget at all? Rope gadget is basically, you can think of it as a function which exists in memory, as in some assembly instructions, and then something that does a return from the function. It doesn't have to be a real function, it can be just some random piece of code in memory which ends with return instruction, and we can still use that. As you can see in ARM, by the way, let's just jump to a random function. It uses also the ret instruction, like it's a different ret instruction, but it's still called ret, so the return instruction. So for example, this could be a rope gadget. Like these 4 instructions, we could, well, 4 instructions and ret. We could actually put the address in one of our what pointers of this instruction, and then this and this instruction will get executed and return will be called. So we have to choose 2 places in memory, 2 places where we have to jump to, and then the consequence of running first the first piece of code in memory, and then the second has to be remote shell, or actually just spanning bash, for example, so we can type cat flag or whatever is necessary. So that's what we have to do. Now, how do we do it? Magic gadget, from what I know, does not exist on ARM, which means we have to use probably 2 gadgets at least to get a shell. Now, normally how you get a shell by using this technique, by using rope exploits, is this way. You first, for example, call a piece of code which sets a register to something of your choosing, then you call another piece which sets another register, and then you call something which takes the address from the first register and stores the second register in memory pointed by that first register. And that gives you writing to memory, and then you can actually create the argument table calling this type of gadgets to execve, and then at the end you can sorry. And then at the end you can actually call execv to execute using the argument table you created to execute bin bash. And that usually takes like 20 gadgets. Now, we do not have 20 gadgets, we have 2 gadgets. So how do we do the same without having 20 gadgets? It's actually, we need to choose proper gadgets. The worst thing is that we do not control any arguments to the gadgets as well, because usually you control the arguments to whatever gadgets you call, you control the things on the stack. So the things on the stack could get popped into registers. We do not have that. We have random stack data and we have random register data. So like the stack pointer doesn't even point close to where our data could be located. And our data could be located in several places. It could be located where, first of all, just before these 2 pointers, right? This area will also contain our data. It could be located on in the buffer for libc. Actually, there is no buffer because they turned off buffering, so yeah, that doesn't work. But, well, wherever it would be located, we do not have access to it because no registers actually point to that memory. So how do we do that? Well, we start with basically magic gadgets. I said that magic gadgets do not exist in this libc, at least I couldn't find one. But that's fine, because what we really need... it's not about what we need, about why do these gadgets not exist. They don't exist because some constraint is not met. That means the gadget exists, but it doesn't work. So what we need to do is we need to find a magic gadget which doesn't work for some reason, and then we need to select another gadget which fixes the constraints, fixes the environment in a way that the magic gadget actually starts working. Now, I basically know which gadgets to choose, and I will choose the proper gadget. I did, while solving this challenge, I choose 3 different magic gadgets. One was in the system, one was some random I found somewhere, and one was in the popen function. System and popen are 2 functions which are known for actually calling bash, like executing bash. If you write code like system something, what it does, it calls bin bash -c and then the something you passed as an argument. Popen behaves pretty much the same way. So if we go to popen and we do not care about that, it actually should call some function here, like ioproc open and whatever. We do not care because we are not going to execute it. As you can see, a fork is going on here, and yeah, I'm looking for exactly this piece of code. This piece of code, what it does, it's, well, setups the argument table. Usually to call something you need to, provide the program name, the arguments, and the environment variables. So that's what you need to call execve, but this is not execve, this is execl. Execl is it's a simpler function. It actually doesn't allow you to do anything automatically. You basically have to hard code the arguments. As in, you give it the binary, and then you give it the arguments, and then you give another argument, and another argument, and another argument, and then the last argument must be null. So you have to have an argument at the end which is null. And it doesn't allow you to set environment variables. You would have to call another function which does that, which is perfect. As I mentioned, the arguments to the functions are in x0, x1, x2. So we need to control probably these arguments, these registers, to be able to influence this. Now, x0, we do not want to control at all. We want this to be set to bin bash, or bin sh, right? And as you can see here in the code, this is exactly what's going on here. x0 is being set to point to the string, to bin sh, because popen needs to do it. This is perfect for us. Now, what's not perfect is that it also tries to set up, like the instructions above, try to set up -c and then something else, and we do not want that. We absolutely do not want this to be called. Which means that the constraint for us, the fix for us, is actually, because we need the null at the end. We need to set x1 and maybe x2 to null, so that there are no arguments passed. I actually thought initially that x1 is enough, but for some reason it didn't work, so my constraint was to set both to null, both must be equal to 0. So that means that we can safely jump into this address here, and then find another gadget. This is the second gadget, what we are looking at. And then find the first gadget, which does this. This is what the first gadget needs to do. Yeah. So how do we find the first gadget? Let's, by the way, note the address of this, because it's going to be important. Oh, and IDA is again trying something funny with me. Okay. So I'm noting the address. This is the second gadget. Gadget 2 is equal to this. Actually, it's equal to libc plus this, because this is the offset into the C library, right? Now, the question is, what is gadget 1? How do we find gadget 1 in an effective way? Now, what you could do is you could do it manually. Since initially the gadgets I looked at, the constraints for the gadgets I looked at were much more severe. They were like x25 needs to point in, well, 21 actually needs to point into memory, which is writable, and x22 needs to point to memory where 0 is located. So, and like x0 needs to be like something. So I decided not to do it manually because, and last year I also didn't do it manually, and I had good experience with not doing it manually, doing it semi-automatically. So let's do just that. Let's do it semi-automatically. And to do it semi-automatically, what you do is you actually emulate the libc in an emulator, and actually you start a gadget in a randomized environment, and then you run the gadget until it either crashes, which is pretty likely in all honesty, or returns, which is a little less likely but still possible for some gadgets, and see what happened. See what's the state of the registers, what you need, what's the state of the environment. Are the constraints met? Does this gadget, which you just called in an emulator, does it meet the constraints? So this is what we are going to do now. And to do that, we basically need to create an ARM, to use an ARM emulator. And I'm using Unicorn. Unicorn is, well, the go-to emulator for several platforms actually in Python, and it's really cool. I really like it. If you don't know it, I fully encourage you to learn it, and yeah, just I guess you can just take a glimpse of what I will be doing here. So I'm going to create a new function which is actually going to be called like, I don't know, find me a gadget, and again the function is going to be work in a loop. It will create the emulator, set up the environment, run the next gadget, check the constraints, and then if the constraints are met, call this go function with the second gadget as the argument. So let's assume that libc we will add, and the full buffer needs to be 48, right? So here we have 8, 16, so that leaves x20 of something. But we need to send. So data is going to be equal to join letter A times 20 hexadecimal, then the gadget 1 and gadget 2, which are actually DQ, which means DQ is this macro, which means take the value and create a 64-bit integer out of it, and so return 8 bytes because 64-bit integer fits into 8 bytes. Gadget 1, gadget 2, and this is the data which needs to be sent. Now we need to send the data. Send all data. I guess we can add this at the end. It doesn't really matter if we add it or not. Now, assuming that it successfully worked, that it actually worked, it might not work because the emulator has its own environment and its own, like, there might be differences between what is running on the server and what is running in the emulator. And I don't mean like in memory differences in C library, but some stuff might not be initialized in the emulator, but would be initialized in a real environment and therefore might behave differently. Some CPU flags might be different in emulator and on the real remote server, and so on. So given this, we should expect it to fail. And that's normal, that's okay. We should expect it to fail. But in the unlikely event of it actually succeeding, what we want to do is we want to send the comments which will output the flag for us. So that would be cat flag. But actually, let's do LA. Yeah. If it didn't find the flag here, maybe the flag is in the top directory. If it's not in the top directory, usually it's in home something flag. Like, yeah. Yeah. Let's start with these commands and actually and so we assume that the shell was actually spawned successfully, and we send these commands, and we will know if the flag is there. Just like we can also add like cat etc plus wd, because why not at the beginning, just to see if everything works, because maybe we actually got a shell but we didn't output the flag, we didn't find the flag, it was not on one of these locations. We still want an indication that it actually worked. So yeah, then we would actually want to read some data. So let's use this to read the data. It will read the data, and the server, if it doesn't work, the server will disconnect, so this will disconnect as well, and it will kill the connection. We do not care about shutdown at this point. What shutdown does, it actually sends the remote site a packet which says, yeah, I'm closing the connection. It's a nice thing to do, but we do not care about that at this point, because the server will probably close the connection if this interact exits. So we already know that the remote site is connected, so we do not need to shut down. Okay, but now we need to find the gadget which we actually want to use, right? Okay, so, well, we need to load the library first. So G is open, what is it called? libc, so 6, read binary, and just read everything into memory. So D contains now the libc, or like libc contains the libc. Okay, now what we need to do is we need to map the memory. So mem map, and what you do is you give the address. So let's do libc address, and let's assume that the libc is going to be located on this address. Yeah, that's a decent address. So libc address, and we need at least the size of libc. What's the size of libc? The size of libc is, sorry, here, 1.5 megabyte. 2 megabytes, yeah. So 2 times 124, 1024, obviously. So now we map the memory for the libc. Now we can put the memory there. So write libc address, and the data is libc. So now we put, keep in mind that this is memory mapped in an emulator, right? Not in the process, in the Python process, but in an emulator under this address. The next thing we need to map is the stack, as usual. So, well, the stack, we know, but the size of the stack is actually pretty random. The address of the stack we don't know, so I don't know. Let's just go with this. It doesn't matter. It seriously doesn't matter. So, yeah, and the size of the stack we know is 3000 hexadecimal. By the way, there is usually another argument here, which is for privileges, but if we do not pass the privilege, then it's RWX, it's read-write executable, which is fine. Again, it doesn't really matter in our case. Do we write anything to memory? Yeah, we need to write the random data. We probably should... yeah, let's... oh, I have OS imported already, so let's go back here. OSU random, I think it's called, and this is the amount, but we need to write it to the stack address. Here we go. I'm going to cheat a little and set the registers not to the values from this memory, but to just random values. Do I have random? No, I don't. Oh, I actually do have this here. So, okay. So let's go back here again. Now I should... I'm going to create another memory area, which is going to be where the code returns in case it actually succeeded, in case it well, was launched successfully. And I'm going to place it here or here, it doesn't matter. Again, just an address, and make sure that they do not overlap, right? We do not want the addresses to overlap, we want them to be in separate memory locations. So, mem map, return address, whatever is enough. I'm not going to write anything there because I do not need any instruction there. I just want to detect from the emulator that the code has reached this return address location, and then stop the execution because I know that, yeah, actually everything worked out fine. Now I need to set the registers, which is reg, I think it's reg write actually, and I do not remember the constants. So what I usually do is I just unpack unicorn and I open it in, so where's the egg file, and I open the constants file, but I don't have the constants file imported. So I import Unicode, but then from unicorn.arm64 const py, not py without py, it's automatically added. I need to import everything. These are the constants for the registers. The file looks like this. And now what you need to do to know about ARM64 is that there are, yes, some registers like W register is actually part of the X register, and what we care about is the X registers because that's what we saw in IDA. We saw the X registers, right? We didn't see any Q registers. I have no idea what a Q register is, but we do need to care about the X register. So, and we actually should mimic whatever, we don't care about libc now, we'll care about it in a second. We want to mimic the way the function, the other function was called. Now I should actually have a function here. Yeah, here it is. So we need to do this in Python code. We need to set this to our gadgets, and we need to set SP to the random value. We do not set SP yet, so let's start with SP. And let's set it to, I think it's like actually the stack address plus 2000 or something like that. It doesn't matter, it just has to point somewhere in a random place. When we are starting to set the registers x0 up to x29 without these two, we need to set, oh actually x30, we need to set all of them to the random data from the stack. In our case, we'll just set it to random data, which means x0 and, sorry, are these consecutive numbers? Yes, 199 is consecutive, so let's do for I in, or like reg in x range. Oh, I can actually turn x range, that's even better. 28. Why is it 28? They are using 30 here. That's confusing. Okay, whatever. Plus 2, I guess. I'm not sure if one of them isn't an alias for a stack register, so I'm going to move my initialization of a stack register later on. Okay, this is 29, 30, but 30 will not be initialized, so this one, this way. Okay. Now, register, and we need to set it to random value. I actually want to set it to random value, because if I wouldn't set it to random value, then, you know, we might find some gadgets which rely on us not setting the registers correctly to random values. Random int, and I went from 0 to, okay, is this 8? Yeah, 64 bits. Guess this is ARM64. So we're setting the registers, and we didn't set correctly the registers that contain the, that are called, right? Because these need to point to our gadgets, which might be important, it might not be important, but it might be important, so that x26 and x25. x26 we know that we need to point to libc address plus, let's see, what was the address again? This one. And the 25 needs to point to our gadget. So yeah, libc address plus gadget. Okay, and then the only thing is, well, there are a couple of things still left to do. Gadget needs to be equal 0. And that's actually not what I want to do. For gadget in x range from 0 to what? Actually, not 0. Where is the text section of libc placed? The text section begins here, and this is the end of it. So, yeah, let's just copy this value and use it here. And the end of it is we need to jump to the next section and copy this address. This is the end of the text section. The text section, we know it's executable. It might contain, it usually contains most of the gadgets. That being said, if you are running short on gadgets, you might want to look on other executable sections because there might be more of them. Even if a section is not marked as executable, do look at the memory, like the page alignment, because the page alignment might actually make another section executable, which wasn't supposed to be. That happens from time to time. Cool. So, yeah, now this is going to this address. This like should be +4 or something, I don't care. At the end, we are not going to find any important gadgets anyway. Okay, we set up everything, now we need to start the emulation. So that's ucemu start, and we start at the location of gadget, so that will be libc address plus gadget. And we end at our special return address. This is where we end the emulation. And we probably want to run at most 100 instructions. Let's go with like 10 instructions, because it gets really random really fast if you start running code for longer than 10 instructions. As in, you, like, most useful gadgets are less than 10 instructions. Oh, can I explain why the page alignment might make a section executable? So do look here. The raw data section is located at this address, right? And it's not set, it's only set as readable. Now, the section before that like for example this load or this one, is set as executable and it's located in the same page in memory. So to make sure, like a page in memory is 4096 or hexadecimal 1000, which means that all of these are on the same, are beginning on the same, and most of these are located on the same section in memory. Which means the memory attributes which have page are aligned to page. That means that you can set readable or writable or executable bit for a whole page, not for individual bytes, but for the whole page. Therefore, this section requires the memory to be at least readable, because stuff will be read from this section, but these sections need the memory to be executable as well, because code will be executed from these sections, which means that the page has to be at least executable and readable. So yeah, which also means that if this page will be set with the executable bit, and this section, which doesn't have the executable bit in the file, is located in this page, in the same page, it will have the executable bit set, because again, the executable bit and the other bits are set per page, with page granularity or page resolution if you want. So yeah, that's why you actually need to be aware of how it's located, how it's actually positioned in memory, and do not fully trust, blindly trust these columns. Okay, so yeah, this is fine. Now we run it, and this is going to throw an exception on us, and I don't remember which exception is going to throw. But so I'm going to catch the exception in a second. Okay, now we need to actually get to know... Oh, one more thing. It will not return to this address on its own. We need to set the return address. The return address is placed in the link registers on ARM and ARM64, so I'm going to place this value there. That means that if a ret instruction is hit, the ret instruction actually jumps to whatever address is in the link register. Okay, now it should return. So now I want to do UC reg read, and I want to read the PC register. The PC is like RIP in x86 is the instruction pointer. And I will, okay, what were my constraints? But my constraints were for x0 and x1 actually be 0. No, x1 and x2. Yeah. Okay, so I need to read these registers back from the emulator after the emulation stops. And if the PC register is equal to ret address, so it didn't crash, it just like actually finished the code, reached the end of the end address. And x1 is equal to 0. And x2 is equal to 0, which are our constraints. This means we found a candidate gadget. The candidate gadget might work, might not work, but it's a candidate which we should try out. So we actually want to print it, because that's what you usually want to do. So let's do this, print gadget, and then the address. Gadget, okay, and then you want to actually try it out. So we want to call go, and then the go with gadget, yeah, and continue. We want to continue because the gadget might not work. The gadget might not work. Like, there might be gadgets, by the way, which are quite funny. For example, while doing the task, I found a gadget which was basically like this: x1 equals x13 by x25. Now please keep in mind that these are registers which have random values, which means sometimes this might be 0, which is perfect, but sometimes it might be 1 or it might be 4, depending on the values in the registers. So each time we call the gadget, we try the gadget, we get a different result. So we have to keep in mind that we might find gadgets which actually are random, and calling them a couple of times might actually solve the challenge for us. Oh, right. Thank you, Dohan, for pointing this out. There's another question. Shouldn't the compiler put raw data on the next page in this cases, right? Shouldn't this be actually aligned to the next page? Yes, ideally it should. Each group of sections, like by group I mean sections having the same attributes, should be in a different page. And the alignment should be set like that. Due to this, for example, on OS X some time ago, part of the text sections were writable. You could actually write to the text section because there was another section in the file close to that which required the write attribute, and that's a really bad thing. So I fully agree, like guessed, but yeah, it should be like that. Okay, so this is fine apart from the fact that this will crash, but we account for it to crash, and we will actually syntax. Sorry, I'm you know, using C++ and Python, intermingling them, and it yeah, sometimes I type the syntax from the second language. Okay, perfect. This is what I was expecting. So here we do try this, then accept, and we yeah, this is what we need to catch. And in this case we just continue. Like continue the execution because we know we didn't reach this this value. Okay, one more thing we want to do probably is we want to here, if gadget is dividable by this value, we want to print that we have progress. So let's print gadget. We don't want to print it with every iteration of a loop because that will slow us down, because the program will have to push stuff to standard output or like have it buffered or whatever. We don't want to do that. Okay, so it's working, but yeah, sorry, like this. Okay, and now what we have to do is we have to wait, and since we have to wait, we can as well answer questions. So let's look at the questions you have. The questions you will see. Oh wait, there. Yeah. What do you mean by gadget? Okay, so I explained this already. How to leak an address if the program doesn't print anything? No write, only read. So this is an. It depends. You probably want to read about blind return-oriented programming. You also want to read about, for example, attacks on ASLR. But the long story short is sometimes if you have code execution, well, if you have code execution, that's easy. If you have only write, there are timing attacks. I'm not sure if the timing attacks can actually be done remotely, in all honesty. Apart from that, it's a good question. Well, if you have, sorry. Again, the question is if you have read, how do you leak something? If you have read, then like you can read from memory, from arbitrary memory, but you cannot print it back. You cannot echo it back. If you can, so it depends, I guess. Because there are two things here, right? First, I just crashed unicorn. Perfect. So yeah, I'm going to start from 0. Okay, let's restart. It shouldn't deterministically crash. It should be non-deterministic. Anyway, so how to leak an address if the program doesn't print anything? I guess it really depends on the case. Sometimes you can do a timing attack, sometimes you can do a timing attack over the network, sometimes you just can't do anything. It depends on the cases, and I don't have any general ideas in my mind. You've shown us that libc starts from zeros and commented that great because we don't need to use math, and right after that you calculated libc as a subtraction. okay, so to explain it, usually what you would have to do is, well, math, you would have to do another subtraction. You would do it like this. You would note from IDA what is the offset where it actually starts, and let's assume this is it actually started as, I don't know, 2 million, right, or 20 million, whatever that is. So you'd have to subtract the 20 million from this first, and then having this, you'd actually receive what we already have here. So you'd need to do another subtraction, and that's it. And yeah, it's the usual conversion from a virtual address into relative virtual address, and then back to virtual address with a different base. I guess basics of reverse engineering, right? What's the progress with Python async? I left some links in the comments, but YouTube hidden my comment. I'm actually going to take a look later on about on the comments and like approve everything. So yeah, but there is no progress. I'm actually like super busy with different stuff right now, but I will get back to it as soon as I'm done. How does this happen that raw data is on page that starts with X? It's the alignment you set in linker, basically. So if you do this, if you compile something, right, you can do gcc-wl-b. Or was this enough? No, it was not. Okay, yeah. If you do exactly this, you can see the linker script, which is being used for compilation. And the linker script has the description how the executable file will look. And you basically want to look at what alignment was used. So is there a default alignment, for example? Blah, 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 start segment. If there's no default alignment, the section will be one after the other, I think. And then some sections are the like constructors, destructors, then there's the data. I'm looking for like, yeah, like this is, for example, like that you have to align a section to a given size. And this is, yeah, another alignment and another alignment for something else. So if that basically means that one section didn't have any alignment and the other was at the beginning not aligned to anything as well. And this is due to how the linker script for a given platform is created, or maybe a custom linker was used. I guess we can check for ARM 64. I do not have ARM 64, seriously. Okay. Okay, I do not have apparently ARM 64, so I cannot check the linker for it. I do have ARM though, so GCC. Yeah, we can check ARM itself. It looks like the same script actually. So there is raw data, there is the text. This is actually funny. This is linker provided variables, global variables, which point to the end of a section. So you can actually use this variable in C to know where the end of your section is in the program, and linker will fill them for you. Yeah, so this is text, then we have fini if it exists, and then there is raw data and there is no alignment in between them, it seems. So that's why this happened, basically. What is thumb mode? And when? Okay, sorry. What's the question on the chat? What is thumb mode? So thumb mode is usually in ARM. Each instruction is 32 bits. So if we actually look at the addresses here, right? Each instruction is like 4 bytes afterwards. Like it's always 4 bytes. And this is typical for ARM. In ARM, all the instructions are 32 bits, which makes really easy jumping into, you know, the instruction boundary, which is not the case on x86, where you do not know if you're jumping into the middle of an instruction, right? Because the instructions are variable size. Now the thumb mode is actually well, somebody figured that 32 bits, 4 bytes for each instruction is just a lot. Like ret instruction. Ret doesn't take any arguments, or, well, in ARM it does, but I think it does, maybe it doesn't. But yeah, let's assume it doesn't, right? So why would you need 4 bytes to encode it? That's quite a lot, and that makes cache expensive and so on, and not well used. Actually, x86 uses cache better in, if you think about it this way, the instruction cache, right? But yeah, so one way to tackle it is actually to create instructions which are smaller. And there are several ways to do it, and one way to do it is called the thumb mode, which is just a special CPU mode where each instruction is being interpreted only as 2 bytes. And to enter thumb mode on ARM, you just jump into an odd offset. So for example, if you would jump not here but on address F41, it would actually also read the code from F40 but in thumb mode. That's how it works on ARM, and then if you would again jump to an even address, it would get interpreted as a normal mode address. So still going, still no results. So I can check if it works actually. So let's just check if it works. I'm going to stop it here. I'm going to copy the address, and I'm going to change the start address to this, and then I'm going to make the constraints a little easier. Like, let's see if it actually reaches this point at any point in time. Yeah. Let's do this, and let's see if we ever reach here without any constraints. Yeah, we do. We reach this place. Let's look for a gadget which actually has only this constraint. Oh, wait, this is fine. I mean, yeah, I'm just going to continue, actually, with all the constraints. And let's look at the questions again. So the second part of the question about the thumb mode was which NDNS is used. ARM actually supports both NDNSs, both the little one and the big one. And I don't actually know how do you set it in ARM. I honestly don't know. I know that it supports 2 NDNS and that's it. Okay. Yeah, we crashed Unicorn again. Okay, regarding the page alignment issue, which causes adjacent sections to share memory permissions, that could be corrected by the linker emitting the binary image more carefully. Right, yeah, that's correct. You can just like set the alignment of sections to something, or you can manually write a linker script to do that. I'm pretty sure there are some options. Like, actually, newest GCC on Linux should output the code with huge space, like 2 MB of space between the text section and the nearest data section by default. I'm not sure why it doesn't do that on other platforms. Oh, it found a gadget, but it didn't work. Is another? Oh, perfect, we got it. Here we go. Gadget, this gadget. And we have pass WD, and then we have the flag. So actually it worked. Yay! Now, HITCON, you found the magic in glibc and get the shell. Perfect. So what we want to do, I guess, is we want to look at this gadget. What is this gadget? By the way, I made a stupid mistake here. This actually should have another parameter 4, which means we should only test every 4th instruction because we don't really care about, entering thumb mode and so on. Well, we could enter thumb mode theoretically, I guess, but yeah, still. Yeah, and we found like 2 crashes and Unicorn at the same time. Anyway, let's look at the gadget we found. We actually need libc for that. And this is the gadget. We actually go here, and everything here gets executed. So it reads some variable in memory, then adds something. Oh, x0, we don't care, probably. Then we move 0 to W2. As I mentioned, W2 is actually a 32-bit part of the X2 register, and probably setting it to something will also like set the upper part of upper 32 bits to something as well. When we read from this memory address, we read into W1, and then we compare it. So it seems that this memory address actually contains a 0, which is lucky for us, and it gets read into W1, and probably the upper is either 0, upper part of the register is either 0, or it's already is going to be well cleared by this instruction. We know it's 0, therefore it will not jump here, but it will return. So at the end, well, we had 0 set to this register and 0 in this register, and we returned, and that's it, that's the gadget. Looking at the gadget, I wouldn't manually find it. Manually, I would be like, yeah, I mean, I have manually no idea what will be on this memory page. I might want to check it, but then I'm not sure when executing it if it's actually the state on the server as well. I'm not sure if this jump is going to be taken or not. I wouldn't use this gadget manually, but as we can see, we did use it. Well, the emulator found it for us, and we could use it. We can actually, going through the next questions, we can actually just keep going and see if there are any more gadgets which are usable just out of curiosity. So let's go, and then I'm going to put this 4 here just to make it a little faster. Okay, so let it run, and let's see if there are any more questions. So, yeah. FAMP2 has also 32-bit. FAMP v2 has also 32-bit thumb instructions. Okay, I didn't know that. Again, I do not know ARM by heart, so you can probably use a lot of stuff to tell me about a lot of stuff which I wouldn't know. Okay, I don't see any other questions, so I guess we can wrap it up. I'm wondering if there are any other gadgets, but actually we are past the middle of the text section. The text section ends at this address, and we are, well, still, you know, A, B, C, D, E, F, then 10 and 11 before that, but we are on the second half of libc, so currently only one gadget was a false positive for some reason, and another gadget actually got us a flag. Okay, I'm going to post this on GitHub as usual, so you can take a look. Then from random stuff, there will be no stream next week, and yeah, probably there will be a short break from streaming for now, because I have some conferences and sometimes I'm, you know, flying out. So yeah, there will be the Google CTF finals this weekend in London. Then there's also the Dragon CTF, main CTF in November. Should be fun. Yeah, it's not finding anything. So that's it actually for today. Please do more CTF pwnables. Yeah, we can think about it. In all honesty, I currently am not doing a lot of pwnables on CTFs. I'm usually doing either reverse engineering or web challenges, sometimes misc challenges, because we have really amazing people doing pwnables in Dragon Sector right now. So yeah, I can do other stuff. But maybe. Okay, so let's wrap it up for today. Again, you can find the code on tab. Oops, wrong screen. This should disappear in a second. Thank you for being here tonight. Thank you to KrzaQ for being my moderator. And see you, yeah, in some time. Happy hacking and best of luck in CTFs if you will be playing any. That's it. I'm going to leave you with some music for a couple of minutes and see you later. Thank you.